All right. With the knowledge of normal coordinate, we're ready to do quantization. So using normal coordinate, Qn, again, n goes from 1 to until capital F. Capital F is the total number of internal degrees of freedom. It is 3n minus 6 for nonlinear molecule. It is 3n minus 5 for a linear molecule. The kinetic energy is 1 over 2 summation sum over all the modes from 1 to capital F Qn squared dot. Potential energy is 1 over 2 summation from 1 to capital F with the eigenvalue of n's normal mode times Qn squared. The center of mass motion, that is the translation, and the overall rotation can be separated from the vibration by separation variable. Actually, we have already done this in the previous lecture. When we talk about separation variable, we use an example of a diatomic molecule to illustrate this separation. In general, for a polyatomic molecule, you can also do this. Translation is rigorously separable from vibration and rotation. That is, the center of mass motion is rigorously separable from vibration and rotation. But actually, rotation, the overall rotation, is not rigorously separable from vibration. Approximately, yes, it is. You can make this additional assumption to assume that you can apply separation of variable to separate vibration and rotation. But actually, in classical mechanics, vibration and rotation are coupled. They do interact with each other. So in quantum mechanics, you can say you have vibrational rotational coupling or vibrational rotational interaction. Classically, this is called the Coriolis force or Coriolis effect. But here, we do not consider that. When you actually consider the higher order terms in your potential, that is, if you do not just truncate your potential to the second order, to the quadratic term, then you need to consider these Coriolis terms. But this is not our purpose, because usually to get a relatively reliable description of the molecule, it's good enough to do just the harmonic vibrational analysis. But for very accurate analysis, for the details of the IR spectrum and for the details of the overtones, then you need to consider a higher order corrections. Okay, so we can write out the vibrational equation. The vibrational equation is 1 over -1 times h bar squared over 2 sigma 1 to capital F partial Qn squared second order derivative with respect to Qn cosine vibration plus 1 over 2 summation from 1 to capital F lambda n Qn squared cosine vibration is equal to the total vibrational energy of the molecule times cosine vibration. So here, the vibrational wave function for the overall molecule, is actually a function of the normal coordinate, Qn. N, again, goes from 1, 2 until 3n minus 6 or 3n minus 5. And Qn, of course, quantum mechanically, Qn is just the coordinate, and in the coordinate representation, the operator Qn is just Qn itself. And the kinetic energy operator for the nth mode is 1 over 2 p Qn squared, right? This capital P is the conjugate momentum of the coordinate capital Qn. And this is, in the coordinate representation, this is negative h bar squared over 2 partial squared partial capital Qn squared. Note that the atomic mass m alpha is not explicitly in the kinetic energy operator. Right? Because let's see, what is the kinetic energy? Kinetic energy is simply 1 over 2 times the coordinate dq dt squared. The mass here is essentially 1, right? So you do not explicitly write out the atomic mass for atom alpha. Right? It's not in the kinetic energy. But of course, implicitly, it actually, indeed, it is contained in Qn, right? Because capital Q, the normal mode, is a transformation from the small q, the mass-weighted coordinate. So the mass of atom actually is hidden inside the small q. All right. So explicitly, you do not have mass, but implicitly, you indeed have mass. All right. So by separation of variable, again here, the overall vibrational wave function is a function of normal mode, and you have f normal modes, right? So if you do assume, you can further use the separation of variable. That is to say, for psi vibration, the overall vibrational wave function can be written as the product of capital F terms, 3n minus 6 terms, or 3n minus 5 terms of psi Qn, right? So this is separation of variable. That means all the normal mode wave functions are decoupled, right? All the normal mode wave functions, you have a set of normal mode wave functions, right? Are decoupled. They are isolated. They are not interacting with each other. This is actually what you can do under the harmonic oscillator approximation. If you consider higher order term in the potential, in the expansion of the potential, then you cannot do the separation of variable, because you will have cross terms in this higher order term, and you cannot separate them. That means when you consider the so-called n-harmonicity, you must consider the interaction between normal modes. But then you ask, what are the normal modes? Well, in that case, when you consider higher order term in your potential, you can still use harmonic normal modes as the basis to expand a general solution for the n-harmonic vibrational wave function. All right. So in that case, you need to consider the interaction between different normal mode wave functions. But we will not talk about that in this lecture, because in order to treat anharmonicity, that it requires more knowledge about quantum mechanics. We need to learn, for instance, perturbation theory in order to do that. Or we need to do vibrational self-consistent field theory or vibrational configuration interaction theory. We haven't talked about this yet, okay? In the later lecture of this course, we will talk about perturbation theory, self-consistent field theory, configuration interaction theory. All right. So under the harmonic oscillator approximation, we can apply the separation variable, and then the total vibrational energy, E vibe, for the whole molecule is equal to the summation from 1 to capital F epsilon n vibe. This epsilon n vibe is simply the eigenvalue for the nth normal mode wave function, right? The whole vibrational equation can be separated into 3n-6 or 3n-5 independent vibrational eigenequations, right? In each eigenequation, you have an eigenvalue, epsilon n, for normal mode n. The total energy, the total vibrational energy is simply the summation of all the vibrational energy, right? And for each vibrational energy, we know it is nothing but a one-dimensional harmonic oscillator, right? It has the same mathematical structure as a one-dimensional harmonic oscillator. Although in this polyatomic molecule system, the one dimension really means the one dimension along this normal coordinate, capital Qn. Capital Qn is actually a linear combination of all the dimensions, right? All the dimensions. So capital Qn characterizes the motion of all the atoms. A normal mode coordinate characterizes the motion of all the atoms in the molecule. But mathematically, formally speaking, it is equivalent to the one-dimensional harmonic oscillator. All right. So the solution can be written as h bar sigma in from 1 to f, capital F, the internal degrees of freedom, capital N plus 1 over 2 omega n. Omega n is the angular frequency, which is square root lambda n. Lambda n is the eigenvalue for the secular determinant. And capital N, of course, this is quantization. So capital N is the quantum number for the nth normal mode, which is 0, 1, 2, 3, etc. Okay. Okay. So what is 0-point energy? 0-point vibrational energy. The 0-point energy for the molecule, for the polyatomic molecule, is just the summation of the ground state vibration energy for all the normal modes, right? And therefore, it is equal to 1 over 2 h bar summation from 1 to capital F omega n, right? For a large molecule, actually, this 0-point energy is not a small number. For a large molecule with a lot of atoms inside this molecule, the order of magnitude of this 0-point energy could be around 1 electron volt. So it's definitely an important factor to consider. All right. So this is the quantization. It's very straightforward, right? Given the background about classical small vibration, about the classical normal modes, classical normal coordinate, it's very straightforward to do the quantization. All right. Next, I want to introduce, I will give you just a brief introduction about the normal mode analysis in internal coordinate. So basically what you do is you just follow the procedure that we talked about previously, right? Then you construct the Hessian matrix, then you diagonalize the Hessian matrix. Internal coordinate, of course, what you need to do is to first construct a set of internal coordinate, and then you transform the mass-weighted coordinate Hessian into the internal coordinate Hessian. And then you do the diagonalization. That's the basic procedure, right? Of course, this procedure is very lengthy. You cannot do it by hand, right? You should write a computer algorithm to implement these steps. And then you can actually pick a molecule with a given geometry. Then you can do the normal mode analysis. Of course, again, the potential energy is given by the electronic structure or by the electronic Schrödinger equation. Okay. So actually, this procedure is pretty sophisticated. It has already been implemented in many computer programs. And you can just pick one of this program and say you do water molecule or CO2 or methane or toluene, whatever. Then you can actually analyze the normal mode. You can visualize each normal mode. You can visualize the motion of all the atoms given a normal mode, right? And then you can analyze for instance, the frequency, 0-point energy, etc. So here, I will just briefly outline the procedure that you need to do in order to actually implement this idea into a computer code. The first step is to actually write down the moment of inertia matrix and diagonalize this matrix. So here, this I is not the identity matrix. This I is the moment of inertia. Matrix. Or sometimes it's called the moment of inertia tensor. If you remember your freshman physics, when you talk about the rotation of a rigid body, I think you have discussed the concept of principal axis of moment of inertia. So if you're not familiar with this concept, you can refer to any book on classical mechanics, or you can actually refer to one of the chapters in Atkins' molecular quantum mechanics. There is a chapter talking about molecular rotations, and then you can learn about moment of inertia. So the first step is, of course, I need to write down this moment of inertia matrix. The matrix element Ij is the summation alpha from 1 to n. Alpha is the index of atom. This is atom alpha, and in total you have n atoms times, then you have, in the summation you have mass of alpha times r alpha squared, delta Ij, the Cronach delta, minus x alpha I times x alpha j. So this is the mass, and this x, this r actually is the position of this atom. Position of atom alpha is a vector alpha, r alpha, and it has 3 components, x, y, z, right? But in general, in order to write a general expression, I simply replace the notation x, y, z with x1, x2, x3. So you have x alpha 1, x alpha 2, x alpha 3. That simply means the x, y, and v, okay? Because in order to write a general expression, I simply replace x, y, z with x, y, x2, x3, right? This is actually quite a normal operation. When you're talking about n-dimensional space, you don't write x, y, z, right? Because you are running out of letters. you simply write x1, x2, x3, x4, etc. to denote each dimension, right? All right. So the first step is, of course, determining the principle of access. The principal axis of the moment of inertia. And this is achieved by diagonalize the moment of inertia matrix, okay? And the X here, the X matrix, is simply the collection of the eigenvectors, right? If you have a real symmetric matrix, then X diagonal is equal to X inverse. All right. The second step is to generate the internal coordinate. So this is done by a linear transformation. So here S is the column vector of the internal coordinate. And Q is the mass-weighted Cartesian coordinate. And D is the transformation matrix. If you start from the regular geometric Cartesian coordinate, then you can use the geometry of the molecule to construct this transformation. That transformation is called the B matrix. And if you start from the mass-weighted Cartesian coordinate, a frequently used implementation in a lot of computer programs is that you first generate 3 translation vectors. So for each translation vector, you simply do, here I just give you a very brief introduction. I'm not gonna talk about the details. So for instance, you have D1, the first translation vector. It's just the square root of the first atom times 1, 0, 0. Square root of the second atom times 1, 0, 0, until you have n atoms, square root of the nth atom times 1, 0, 0. And this gives you the column vector for the x dimension. It's denoted as D1. The x dimension, because 1, 0, 0 is the unit vector along the x direction. So what is D2? D2 is for the y direction. So instead of 1, 0, 0 here, you just do 0, 1, 0. So D3 is for the z direction. Instead of 0, 1, 0, you do 0, 0, 1, 0, 0, 1. So you construct the 3 translation vectors. And then you need to construct the overall rotation vector. It could be 3, it could be 2, depending on whether or not your molecule is linear or not. If it's a linear molecule, then you have 2 overall rotation. If it's nonlinear, then you have 3 overall rotation. The construction of the overall rotation vectors require the computation of the X matrix. Here, this is the X matrix in your first step, and the atomic coordinate matrix with respect to the center of mass. And then after that, you can use the Gram-Schmidt procedure to construct the rest of the D vectors, the column vectors. So you use this Schmidt orthogonalization to make sure the rest 3n-6 or 3n-5 vectors are orthogonal to the translational vectors and overall rotation. So the third step is to construct the Hessian. You need to construct the Hessian matrix in the internal coordinate. This Hessian is called F internal coordinate. So we do this transformation by simply do this projection. So this F MWC is what we have talked about in the first section. That's just the mass-weighted Cartesian coordinate Hessian matrix, right? So in this matrix, each element is nothing but the second-order partial derivative of the potential energy with respect to Qi and Qj, right? So this D is just a transformation matrix that we constructed in the second step. By doing this, we essentially effectively project the overall translation and the overall rotation out of this 3n by 3n Hessian matrix. And the next step is, of course, you diagonalize this internal coordinate Hessian matrix, right? You do diagonalization. This means you do right? Diagonalization means you do this transformation. Here, this L, again, is the collection of the eigenvectors, right? This capital lambda, Greek letter capital lambda, is a diagonal matrix. On the diagonal elements, you have what? The eigenvalues, right? You have F eigenvalue. F is in internal degree of freedom, the number of internal degree of freedom. And since it's a diagonal element, it's a diagonal matrix, all the other elements are simply 0. And the next step is to do, then you have, of course, you have lambda, of course, then you have normal mode frequency, right? Usually, normal mode frequency is expressed by using linear frequency. So this is the angular frequency over 2 pi. The angular frequency is square root of lambda over 2 pi, right? And of course, the eigenvalue do not depend on whether or not you choose mass-weighted coordinate or internal coordinate, right? The eigenvalue, or in other words, the frequency, are the intrinsic properties of the molecule. Of course, conventionally, people use this internal coordinate to do the calculation because it's more efficient. But of course, if you want, you can still do the calculation in the Cartesian coordinate. Conventionally, for the unit of this frequency, people use the wave number. Okay. The SI unit for the frequency is per second, but it's very easy to convert per second to this wave number, which is per centimeter. This is usually the unit you use in IR spectroscopy or in Raman spectroscopy. Now you have normal mode frequency. Of course, you can also have the eigenvectors, the normal mode eigenvectors. Right? The eigenvectors is all the eigenvectors are collected in this matrix L, right? So L1, L2 until LS, right? All of this L1, L2, LF are just what? Are just the column vectors, right? They're just the column vector. For instance, L1 is a column vector in which the element is L1K, right? The case row is L1K, right? What is L1K? This is the normalized amplitude or normalized displacement for the case coordinate in normal mode 1, right? So L, this matrix, is used to diagonalize the Hessian. All right. So the next step is, because we want to visualize the motion of the atom, right? You want to see the animation for the vibration. When you visualize it, you're doing it in the regular geometric Cartesian space, right? So the next step is to convert everything back to the regular geometric Cartesian coordinate. So convert everything back to the regular geometric Cartesian space or Cartesian coordinate. Okay, so how to do this conversion? Well, it's pretty straightforward. Now, lambda, capital lambda, is your diagonalized matrix, right? This is your diagonalized matrix. If you plug in this transformation, you apply it in step 3 back into step 4, then what you do is lambda is, you have this transformation, right? Times d f mass weighted coordinate d l internal, right? This term in the middle is what? This is nothing but the internal Hessian, or the Hessian matrix in terms of the internal coordinate, right? So you have, this is diagonalization, right? L internal times F internal times L internal is nothing but the diagonalization of the internal coordinate Hessian, right? And of course, you can combine L and D together. You will have a small L diagonal matrix MWC times F MWC times small L MWC, right? Because if you look this, terms times this term, the middle term, the mass weighted coordinate Hessian times another term, this is again in the diagonalization form, right? You're diagonalizing the mass weighted coordinate Hessian with the mass weighted coordinate eigenvectors, right? Right. So this is nothing but d dot the internal L, right? This is the matrix that you use to diagonalize the internal coordinate Hessian. And you apply this transformation matrix D on this L internal coordinate eigen matrix. Then what you get is, of course, the mass weighted coordinate. The next step is actually to calculate the so-called L Cartesian. This is defined, again, this L Cartesian is a matrix. It's a collection of the eigenvectors of the nth normal mode. So this is calculated as the mass matrix times this L matrix, the mass weighted coordinate matrix L. So let's talk about the units here. So actually, here the unit for D is, let's talk about the unit here. D is the transformation matrix, right? So the unit for Q, which is the mass weighted coordinate, is by definition, it has the unit of square root mass, right? And the unit for D is actually, it's constructed in a way so that it has the unit 1 over square root of the mass. So the internal coordinates are dimensionless quantities. And L internal coordinate, the matrix element is essentially the normalized amplitude, right? And the normalized amplitude has the same unit as the mass weighted coordinate, right? So in this case, L contains the unit square root of the mass. And therefore, if you do D matrix dot the L matrix, then you do not have any unit, right? This is the small l mass-weighted coordinate, right? So you do not have any unit because 1 over square root mass times square root mass is a dimensionless quantity. So really, for LMWC, it's a dimensionless quantity. Or I should say, each element inside this matrix has no unit. This mass matrix is actually defined as a diagonal matrix. Its matrix element is defined as KK. Well, since it's diagonal, we can write, say, KK prime. This is just actually delta KK prime over square root MK. So, of course, this is diagonal. On the diagonal element, K is equal to K prime. You can say MKK is equal to 1 over square root MK, right? MK is the mass associated with the case degree of freedom, or the case coordinate. Okay, so therefore, this L-cart, this matrix, it has its matrix element has the unit of 1 over square root mass. Okay, all right. And of course, if you consider the nth column vector inside this L Cartesian matrix, well, again, the L Cartesian matrix, right, it's a collection of the column vectors, right? Here you have F. And for each column vector, it is for the nth normal mode, right? Here, this means the nth normal mode. And this is a column vector. It actually represents the displacement of all the atoms inside the molecule at the given mode n, right? So it will have many entries. The first 3 entries are for the first atom, right? And the 4th, 5th, and 6th entry are for the second atom, right? For atom 2. This is delta x over m2 square root, delta y over m2 square root, delta z over m2 square root, right? And you have multiple entries, right? In total, you have n atoms, and therefore you have 3 n entries here. The last entry, the last 3 entries are for atom n. This is delta x over mn square root, delta y over mn square root, delta z over mn square root. All right, so then we can define the so-called effective reduced mass, mu n for the nth mode. For each normal mode, we can assign an effective reduced mass. It's like what we have in a diatomic molecule. For diatomic molecule, because you only have 2 atoms, therefore you only have 1 non-zero frequency vibrational mode, right? So the reduced mass is simply m1 times m2 divided by the total mass of the diatomic molecule. So here you have a polyatomic molecule. So you cannot define the reduced mass by using two atoms. Okay, you cannot define the reduced mass by using two atoms that are connected by a chemical bond. You have to generalize the definition of the reduced mass. And the generalization is actually, this is simply L Cartesian for the nth mode complex conjugate times L Cartesian for the nth mode. So this is an inner product. And then you put this term on the denominator. All right? Because again, the unit of L Cartesian is actually 1 over square root. This is 1 over square root m times 1 over square root m. And this gives you 1 over m. And because this term is on the denominator, and therefore the unit of this reduced mass, of course, is the unit of the mass, right? So it has the unit of mass. All right. And here, of course, you have this complex conjugate. If it's a real, if it's a real matrix or a real element, a real column vector, all the elements are real, then this is nothing but the transpose. Okay? If L Cartesian n is real, then L complex conjugate Cartesian n is nothing but the transpose. Sometimes in linear algebra, we simply write LT. This means the transpose. You exchange row and the column. Okay. So if it's not real, for instance, then what you do is you do a complex conjugate for all the elements, and then you do the transpose. Sometimes A complex conjugate is also denoted as AH. This H means the Hermitian transpose. The terminology conjugate transpose is equivalent to Hermitian transpose. If the Hermitian transpose is equal to this matrix itself, then this A matrix is called the Hermitian matrix. Okay, the Hermitian transpose is an operation you can do on the matrix. Hermitian matrix means a type of matrix that satisfies Hermitian transpose being equal to itself. And then we can define the force constant for mode n. This is Kn. Kn is defined by omega squared times mu n, right? So this force constant is, of course, defined for a particular normal mode. It's not defined for a pair of atoms that are connected by a chemical bond, right? Unlike in diatomic molecule, you only have two atoms, and therefore you only have a non-zero vibrational normal mode. And therefore, the force constant there is just the force constant of the spring that connect these two atoms. But for a polyatomic molecule, you cannot do that because the normal modes represent the motion of all the atoms, right? It's not just the motion of two particular atoms. So this is really a generalized concept for the force constant, right? So again, I want to emphasize that for polyatomic molecules, the force constant Kn is not defined for a particular bond. It's not the stiffness for a particular spring. Kn is defined for a particular normal mode. The normal mode includes the motions of all the atoms. This can be viewed as a generalization for the diatomic force constant. So in this part, we have basically covered a brief overview about how to actually implement the normal mode analysis by using internal coordinate.